Okay, we're going to continue with 10.3 notes. We're going to revisit particle motion. So now we're going to consider horizontal and vertical. We're considering x prime of t and y prime of t in terms of horizontal and vertical velocity component vectors. So x prime of t, we can also think of it as dx over dt. This is the rate at which the x coordinate is changing with respect to t, or the velocity of a particle in the horizontal direction. We can also think of this as horizontal velocity. Y prime of t, or represented as dy over dt, is the rate at which the y coordinate is changing with respect to t, or the velocity of a particle in the vertical direction, vertical velocity. Okay, and we have these components. We can think of these position vector, velocity vector, and acceleration vector with these arrows on top. And we can put them in parentheses, or we can put them as components in angle brackets or chevrons. And both would represent the position vector or component of the position at any time t. And the velocity vector or velocity components of x prime of t and y prime of t, this will represent velocity vector at any time t. And then x double prime of t, y double prime of t, represented by the vector a, would be the acceleration vector at any time t. And the vectors can be contained using parentheses, or sometimes you may see these chevrons or these angle brackets to close to give as notation. All right, dy over dx. This is the rate of change of y with respect to x, or the slope of the tangent line to the curve, or the slope of the position vector. And then d2y over dx2, this is the rate of change of the slope of the curve with respect to x. So we've seen all this before from the last set of notes, but now we're going to be, we're looking at these through the lens of particle motion. All right, so next, the absolute value of the velocity. Right, we know the absolute value of velocity is speed, and we can represent that using this resultant vector. And if you see the double bar, v of t that represents speed, and we could think of speed of the particle as the magnitude or the length of the velocity vector. So basically finding the distance, or finding the square root of x prime of t squared plus y prime of t squared. Okay. Now, if we accumulate this over two intervals, then we have the length of the arc, or the distance traveled. So let me go back to here, though, that this can be represented as speed of the particle, but sometimes you may see the word magnitude, or length, or the norm of the velocity vector. So all these words can represent the same thing with speed. And if we take that value, and if we find the integral between two endpoints, then we have the length of that arc, or the total distance traveled from particle A to B. All right, remember that the absolute value, the integral of absolute value of v of t, is the total distance traveled, whether it is along a straight line or a curve, right? So this is where, whether we're going forwards or backwards, we're counting all the negative portions below the curve as positives as well. So in much the same way, you can think of the integral of speed being the total distance traveled along the curve. Think of it as arc length. But if you just see the integral of velocity, right, without the absolute value bar, just velocity, then that's the displacement, where we are taking the net change in the position where we have to incorporate positive and negative values, and where positive and negative values will cancel each other. Okay, net change in position. Okay, let's look at the final two examples here. Example 5, a particle moves in the xy plane so that at any time t, where t is greater than or equal to 0, the position is given by x of t and y of t. So our position vector, s of t, s arrow of t, we can write these as the x of t and y of t components. So t cubed plus 4t squared and t to the fourth minus t cubed. And if we want to find the position vector at 0, we can just plug 0 in for t, and that will be 1 plus 4, which is 5, and 1 minus 1, which is 0. So here's the position vector at the time t equals 0. Okay. So for B, it says find the velocity vector at t is equal to 1. So to find the velocity vector, we simply find x prime of t and y prime of t. So x prime of t, t cubed becomes 3t squared. 4t squared becomes 8t. So that's the x prime component. And then the y prime of t, or dy dt, we find the derivative 4t cubed minus 3t squared. And then if we want to find the velocity vector at t equals 1, we simply plug 1 in for t, and we get 3 plus 8, which is 11, and 4 minus 3, which is 1. Okay, part B, the speed of the particle. So speed of the particle is simply the square root of my x prime of t squared plus y prime of t squared. So x prime of t squared, in this case, evaluated at 1 is 11. So 11 squared plus 1 squared is square root of 122. So we can think of this as also the resultant vector with the horizontal and or the hypotenuse created from drawing the horizontal component vector and the vertical component vector. Part C, the acceleration vector. So the acceleration vector is simply x double prime of t and y double prime of t. So the derivative of x prime of t would give us 6t plus 8. And then the second derivative, 4t cubed becomes 12t squared. 3t squared becomes 6t. So now my acceleration vector evaluated at t is equal to 1. Simply plug 1 in for the t value. So 6 plus 8 is 14. And then 12 minus 6 is 6. So here we see that this particle is picking up speed faster horizontally than it is vertically, even though they're both increasing. Okay, example 6. A particle moves in the xy plane. So this is not linear motion. This is vector and parametric motion here. We have x is equal to root 3 minus 4 cosine t, and y is equal to 1 minus 2 sine of t. And we have our endpoints where t is between 0 and 2 pi. So we find dy over dx. So dy over dx, again, we can think of this as y prime over x prime. So y prime, we simply identify y and find the derivative. 1 goes to 0. Negative 2 sine of t becomes negative 2 cosine of t. So there's my y prime. So to find x prime, or dy over dt, we find the derivative of x. Root 3 is a constant that goes to 0. Negative 4 cosine of t. Cosine becomes a negative sign, so the two negatives will cancel out to be a positive. So we're left with 4 sine of t. And this is my dy over dx, which I can clean up a little bit more to be negative 1/2 cotangent of t. So cosine over sine is cotangent. So now I have my dy over dx. Now I want to find the second derivative, d2y over dx2. Now if we think about our formula for d2, our second derivative, we're finding the derivative with respect to t of dy over dx all over dx over dt. So we talked about where and how this second derivative formula was created. So the derivative of dy over dx, we simply look at our previous result. So we just want to find the derivative of negative 1/2 cotangent of t. Well, let's see. Cotangent of t becomes negative cosecant squared of t. And there's already a negative here, so the two negatives will cancel out to be a positive 1/2 cosecant squared of t. And then we keep the x prime of t without changing it. That's the dx over dt, which is 4 sine of t. And then these two can combine a bit more, bring the 4 up to the top. we can make this negative 1/8, and then bring the sign up to the top, flip it to become cosecant as well, and then we can make this 1/8 cosecant cubed of t. Part B, the path of the particle intersects the x-axis twice. Write an expression that represents the distance traveled by the particle between the two x-intercepts. Do not evaluate. Well, let's think about this. Particle will intersect the x-axis whenever the y is equal to 0, right? Whenever the y is equal to 0. So we simply need to find out where y is equal to 0. So we take our y component, set that equal to 0. So 1 minus sine of t, set that equal to 0. Let's solve for sine of t first. So bring over the sine of t, move over to 1, divide by 2. The two negatives cancel out. So we've got to figure out, when is sine equal to 1/2? Well, sine is positive in the first and second quadrant, and 1/2 will be variations of pi over 6. So pi over 6 in the first quadrant and 5 pi over 6 in the second quadrant. So this provides our bounds. Okay, distance traveled is simply arc length, right? And the arc length formula is just a definite integral of pi over 6 to 5 pi over 6 square root of x prime squared plus y prime squared. And the x prime we found was 4 sine of t. Y prime we found was negative 2 cosine of t. And the problem just says write the expression that represents the distance traveled, but do not evaluate. So here is our expression without evaluating.